Hi everyone, Miss Nelson here, back with another remote lesson for Unit 9. Our objective for today is how do we know the Earth rotates? For your do now, I have two questions. One, how long does it take for Earth to rotate once? So that's for Earth to do one full rotation. And secondly, what direction does it turn? I'm going to put 1 minute on the clock for you guys to answer these questions to the do now, and then we'll discuss them. All right, on your marks, get set, go! Boom! Time is up. So let's look at the answers. 1. How long does it take for Earth to rotate once? Well, a day. Okay, technically, if you looked at your Earth science reference table, 23 hours, 56 minutes, and 4 seconds. But basically, a day. In what direction does it turn? If you're looking down at the North Pole, it would appear to turn counterclockwise. In fact, everything in the solar system both rotates and revolves counterclockwise. So, our objective for today is how do we know the Earth rotates? How do you know the Earth rotates underneath you? We certainly don't feel it rotating underneath us. We don't feel like the Earth is moving underneath us unless you're at an earthquake. So how do we know the Earth rotates? Any ideas? Any ideas out there? Anyone? Well, there are two things that we've talked about so far. One, the sun moves across the sky every single day. And secondly, the stars appear to move around the North Star or the star Polaris. But this is not strong evidence for Earth's rotation. If Aristotle was here, he might say, well, the sun and the stars could just be moving around Earth in the sky. How do we know that the Earth is rotating? The mathematician Ptolemy also proposed the same idea. So, in fact, they believed in what's called the geocentric model. So the geocentric model is a theory that everything revolves around Earth. So the fact that the sun rises and sets would not be that Earth rotates in the geocentric model. It would be because that the sun is moving around Earth. Same things with anything else in space. The heliocentric model is the theory that the sun is in the center of the solar system and everything else revolves around the sun. So how do we know which model is correct? Well, we need more evidence. So the first piece of evidence that I'm going to give you for Earth's rotation is called the Coriolis effect. If we take a look at this GIF, that black ball is going to drop straight down. Originally, the red dot was right underneath the black ball. But because the whole disk was rotating, the ball didn't hit it. If we look at the GIF underneath, the diagram underneath, if we're looking at the perspective from the red dot, so if you're standing on the red dot, you're going to see that the ball appears to rotate on a curved path. So even though it's going straight, because the disk is moving underneath it, it appears from the people on the disk that the black ball goes on a curved path. This is called the Coriolis effect. So the Coriolis effect causes wind and ocean currents to curve related to the direction of travel, or at least appear to curve. In fact, if we look at our planetary wind and moisture belt diagram in our Earth Science Reference Table, we can see that those paths curve. And the reason they curve is because of the Coriolis effect, which is because the Earth rotates. If we look just in the northern hemisphere, so just up here, we can see that if you're following in the direction of the path, those paths appear to curve to the right. Whereas if we looked in the southern hemisphere, if we choose any path to follow, if you follow along that path, it will curve to the left or bend to the left. So in New York, which way does the path bend? Well, first we have to think, where is New York? New York would be right about there, between the 30 degrees north and 60 degrees north latitude lines. And right there, if we look at those paths, the paths of the wind appear to bend to the right. So in New York, the path bends to the right. Now, we're going to imagine you are traveling in a wind current, say on an airplane, and you're traveling along any one of those four paths that you see to the right as the Earth is rotating underneath you. How would your path look on a stationary Earth? Remember, in the northern hemisphere, the paths bend to the right, and in the southern hemisphere, the paths bend to the left. All right, I'm going to put another minute on the clock. You have a minute to see if you could draw, from the starting points of those arrows, how the path would appear to bend. On your marks, get set, go! All right, time is up. Let's see. So we're going to start with this arrow. And remember, we're going to pretend that we are walking along that path, but curve over to the right. So if we're walking along that path, walking down, and we start turning to the right, we are going to go in that direction. Whereas the other one in the northern hemisphere, now we're walking straight up. And if we curve to the right, we would curve in that direction. Now let's look in the southern hemisphere. In the southern hemisphere, we're going to bend to the left. So if we're starting near the South Pole, walking north, and we bend to the left, it'll appear to go in that direction. And if we're starting near the equator and walking south in the southern hemisphere, and we turn to the left, we would be turning in this direction. These are how the paths appear to bend in the different parts of Earth and in the different directions. And this is all due to the Coriolis effect, which tells us that the Earth is rotating underneath our feet. But that's not our only piece of evidence. The other piece of evidence that we have for Earth's rotation is called the Foucault pendulum. So here's a video of a real-life Foucault pendulum. As you can see, you have this big metal ball that swings back and forth. And if you look at the video, you could see that it's just about to hit that one peg. And in fact, it has already knocked down many other pegs along its path. And that's because this ball slowly turns in a circle as it goes around. So the Foucault pendulum swings straight back and forth. But because Earth rotates underneath it, the pendulum appears to change its direction of swing. If we look at the Foucault pendulum from space, we could see that, as you can see, the Foucault pendulum swings straight back and forth as Earth rotates underneath it. But now let's travel with Earth. And now we see that it appears like the Foucault pendulum is swinging in a circle. It's not. It's going straight back and forth in space, just Earth is rotating underneath it. But from the perspective of Earth, it appears like it's going in a circle. So over the course of a day, that metal ball swinging straight back and forth will knock over all of the pegs because the Earth is rotating underneath that ball going straight back and forth. Believe it or not, there is a Foucault pendulum nearby that, if it wasn't during the COVID-19 pandemic, I would tell you all to go out and see. It's at the Children's Hospital in Montefiore. So if you look in this picture map on the right, there's Roosevelt High School, and kind of near Van Cortlandt Park is the Children's Hospital at Montefiore. And inside their lobby, they have a Foucault pendulum that you could see. But I hope that none of you have to go see that Foucault pendulum or have to go to the hospital during this time. So stay at home, stay safe, but when this is all over, go check it out. All right, now I have 2 exit ticket questions for you. First, which model correctly describes how the Earth, Sun, and the other things in space move? Was it the geocentric model or the heliocentric model? And second, what are the 2 strongest pieces of evidence for Earth's rotation? Please remember to send a picture of your notes and the exit tickets to Miss LaPlaca on Remind. And I hope you guys are all well and safe, and I really miss you. All right, hope you guys are all good, and I'll see you later. Bye.